Everybody, it's a huge pleasure to have today with us John Terning from UC Davis. So let me briefly introduce John. So John did his PhD in Toronto University. He then did a batch of postdocs. He moved around quite a lot, Yale, Boston, Berkeley, Harvard. After that, he got a senior position at Los Alamos, and after a few years, he ended up at UC Davis. So John is a very famous scientist in our field. He's the author of more than 130 scientific papers, and he also wrote 3 books. So the first one is Modern Supersymmetry. Then he wrote Extra Dimension in Space-Time with Isaac Bars. And quite recently, I think just a few years ago, he wrote Quantum Physics, Mini Black Holes, and the Multiverse together with Yasunori Nomura and Bill Poirier. So today he's going to tell us about the magnetic monopole 19 years later. So John, please.
Thanks. I'm really happy to be here. So the plan of the talk is to spend about half the time just reviewing what the ancients up to the year 2000 knew about monopoles. And then the last part of the talk, there were 3 outstanding problems with monopoles that people didn't understand, and only in the last 3 years have they been figured out. So most of the talk is about the first, 70 years, and the last part is about the last 3 years. Okay, so not advancing. Is it not working? I can do it the old way. So the first time people looked for monopoles was, at least written down, was 1269. Peter the Pilgrim, he called himself, was laying siege to a city in Italy. And as you know, laying siege is a lot of boring, waiting around for people to submit. So he had a lot of time on his hands, and he decided to write a little book about everything he knew about magnets. And one of his experiments was to take a magnet, which has 2 poles that we would call north and south now, cut the magnet in 2 so he could get a north pole and a south pole. And what he found is that he got 2 dipoles. Each part has a north pole and a south pole. So that was the first time people failed to find the monopole. Next up is Gauss in 1833. He wanted to know how much work it takes to move a unit magnetic charge, which is a monopole, around a current loop. So we have this black thing has a current flowing through it, a current I. It goes on some curve C prime. Then I move my monopole along curve C. And he wanted to know how much work it takes to do that, to go around the curve. And so, just integrate the magnetic field at the position of the monopole along the curve that you move it on. Biot-Savart tells you how to calculate the magnetic field of this current loop. So you just have to do this horrible integral. He said, oh, enough of that. Let's try it another way. If you use Stokes' theorem, you can write this integral around the curve as integral over the curl of the magnetic field dotted into the surface, the Stokes surface. He didn't actually have Stokes' theorem in 1833, so he had to work it out with geometry. But he's Gauss, so he can do things like that. And then using Ampere's law, you can write curl B as the current density and then integrate it. You get 4 pi times the current times the number of times the wire goes through that Stokes surface enclosed by the curve C. So you can rearrange this now and get an equation for m, the number of punctures of the Stokes surface. M is this horrible double integral over 2 curves of this nasty-looking thing. And this is the first topological number in anywhere, not just physics, but in all of math. And he didn't think it was important enough to actually publish, so it was just found in his note papers after he died. But this is the famous linking number, which will play a role for us later on. Next up is Mr. Heaviside. Some people use Heaviside units. You heard about Heaviside units, right? Heaviside noticed that if you have Maxwell's equations, if you're in vacuum, If you take e to b and b to minus e, then you get back the same equations. This is what we call electromagnetic duality. I've written it here for the experts in terms of covariant field strengths. If you don't know what a covariant field strength is, just ignore any equation with an F and look for the E's and B's. It's the same thing. Okay, J.J. Thompson, we're up to the 1900s. J.J. said, let's take an electron and a monopole, have them sitting at some positions. Let's calculate the total angular momentum in the electromagnetic field. Not something you'd normally think of, but he thought of it. And he did it, and he found that the magnitude of the angular momentum in the field is the electric charge times the magnetic charge. And that angular momentum vector points from the electric charge towards the magnetic charge. So that's kind of crazy. Just static things sitting there have angular momentum. No one's impressed. I was impressed. OK, so the big thing is Dirac. It's 90 years since, well, 91 years since Dirac figured out how monopoles work with quantum mechanics. So in quantum mechanics, you know we need to talk about potentials if we want to solve any equations. So we needed to find a vector potential that gives a magnetic field. Magnetic field is curl of the vector potential. And he figured out that this horrible thing gives you a magnetic field that's pointing out, just like the Coulomb field of an electric charge points outwards in all directions, falls off like 1 over r squared. But it depends on some vector n. You have to choose some direction, and then you can write down this thing. Then the magnetic field doesn't depend on n, so you could choose any direction you wanted. But the potential depends on n. And the potential matters in quantum mechanics because Dirac could have said, you know, in 30 years, Aharonov and Bohm will explain that if you move an electron through a potential where there's no fields, you'll pick up a phase, the Aharonov-Bohm phase. And Bohm was in Sao Paulo at one point, so everyone knows this story here. So the Aharonov-Bohm phase of the electron, when it goes around this singularity, you see this blows up if r is proportional to the vector n. You get infinity. So there's a singular line. That's what we call the Dirac string. If I move the electron around in a circle around that string, I'll pick up a phase. Now, that string isn't really there, right? It's just some arbitrary gauge convention that he chose. So it should be undetectable. So to be undetectable, that means the phase has to be a multiple of 2 pi. And to make the phase a multiple of 2 pi, you have to have the electric charge times the magnetic charge is an integer over 2. That tells you that electric charge is quantized. If there's one monopole in the universe, all electric charges are quantized in terms of a basic electric charge. And you've heard that all electric charges are quantized in terms of a basic electric charge. And so this is really the only explanation of why that would be. Later, people developed grand unified theories, and it comes out of that that charges are quantized. But in those theories, you're guaranteed to have monopoles, as we'll see. So monopoles are always at the heart of charge quantization, as far as we know. If someone has another explanation, publish it. You'll be famous. Oh, I have to run back. OK, 1969, Schwinger, Nobel Prize winner, came along and said, well, I could imagine I have particles that have both electric and magnetic charges. Why not? And because he had a classical education, he came up with a fancy name, dyons. And then if you have 2 dyons, the thing that's quantized is electric charge of 1 times magnetic charge of 2, the second particle, minus the electric charge of 2 times the magnetic charge of 1. That has to be a half integer. Oh, and I should have said, this is just like this charge quantization of Dirac. E times G is a half, or a multiple of a half. J.J. Thompson already told us that angular momentum is E times G. quantum mechanics tells us that angular momentum is quantized in units of half. So E times G from angular momentum quantization has to be a half. And the same thing for dyons, because there's the same, that's the formula for angular momentum in that case. OK, we're rolling very quickly. 1976, 't and Mandelstam. So remember, there was this electromagnetic duality. E goes to B, and B goes to minus E. So they realized that if you had a magnetic condensate, that would confine electrons. So magnetic condensate, think about a superconductor. The proof is, let's do the proof first. Maybe it'll make sense then. Proof is the superconductor has an electrically charged condensate, right? The Cooper pairs make an electrically charged condensate. That breaks the gauge symmetry inside the superconductor. So particle physicists would say that inside the superconductor, the photon has a mass. Condensed matter physicists would say there's a penetration depth. So for a photon to get inside the superconductor, it gets exponentially damped unless its energy is above that mass scale. So when we have a superconductor, we don't have magnetic fields inside. But what if I had a monopole and an anti-monopole inside a superconductor? What happens? So you may have seen that superconductors can have tubes of magnetic flux punched through them. So if I have a monopole and an anti-monopole inside a superconductor, all the magnetic field between them will be concentrated in a tube. And that means as I pull them farther apart, that energy grows with the length. Energy growing with length is a potential that doesn't have any free states, right? Every state is a bound state. So that's confined. And then by electric magnetic duality, replace Cooper pairs of electrons with Cooper pairs of monopoles, and replace monopole anti-monopole by an electron and a positron. If you don't believe that story, well, then there's no hope for this talk. If you don't believe that story, Seiberg and Witten, as we'll see later, came up with an exact proof or calculation of an exact results in a particular quantum field theory that says exactly this. So this is really true. OK, here's a biggie. So around the time people were thinking of guts, what are guts? So in the standard model, there's 3 forces. And for shorthand, we call them SU3, SU2, and U1. Does anyone not know what I mean by that? Everyone here is a particle theorist. I thought there were supposed to be some astros. No? No? Everyone knows exactly what I'm talking about. OK, so at a gut, we take all 3 of those groups and put them in one single group. And then that is a gut. So there's only one type of force. And then some Higgs comes along and messes it up and gives us the standard model. So there's some Higgs that is breaking our gauge symmetries. So 't and Polyakov looked at a very simple case. Just take the simplest non-abelian group, SU2, and put in Higgs in a triplet representation for the experts. But you can Higgs it down so you break SU2 to U1. U1 is electromagnetism. So you can take horrible non-abelian theory that you don't understand and break it so it's just electromagnetism, which you do understand. At least if you read Jackson, then you understand it as much as anyone does. So in that theory, what they found is there are weird solutions. There are hedgehog solutions. So if there's a point where the Higgs is like the condensate in the superconductor, right? There's a point where the condensate or the Higgs vanishes. There's a solution where it grows away from that point, and the direction in space is correlated with the direction in SU2. SU2 is like SO3, so you can do things like that. So that's this cartoon of a hedgehog. The field directions in the non-abelian space correlate with the directions in physical space. So this hedgehog is a stable solution. And when you calculate its properties, you find it has a magnetic charge. So even if you didn't have a fundamental monopole lying around, you could just make one by taking your SU2 gauge theory and Higgsing it in a certain way. And so the consequence of that is that any single group that breaks down to electromagnetism, a U1, always has to have a monopole solution. So if there really are grand unified theories in nature, then we're required to have monopoles somewhere. So that's when people got very excited about monopoles. Up until then, it was just theorists goofing around. Now it's serious, because everyone believed in grand unified theories. So here's Mr. Witten, Ed. He likes to be called Ed sometimes. Ed Witten showed that if you have a monopole, something interesting can happen when you also have a CP violating term. So what is the CP violating term? So the black is for experts. If you're an expert, you know what that means. If you're not an expert, look at the blue line below it. The first term, this is a Lagrangian for electromagnetism. So in the Lagrangian, you have E squared minus B squared. In the Hamiltonian, it's E squared plus B squared. So those are rotationally invariant. There's another rotational invariant you could write. You could write E dot B. That's what that F star F is supposed to mean. So if you wrote E dot B, that's rotationally invariant. You stick a parameter in front of it, call it theta. You don't normally write that because it violates charge conjugation in parity. So parity flips the sign of directions. So it makes left-handed turn into right-handed. Charge conjugation takes positive charges and makes them negative charges. So normally, you'd like to think that that's a symmetry of electromagnetism. It's not a symmetry of nature, so why not have a term like that? So if there are no monopoles, that term is totally harmless. It doesn't change anything. But if there are monopoles around, weird things happen. And one of the weird things that happens is that if I have a dion, say, with charge Q, electric charge Q and magnetic charge G, then when I actually measure the electric charge of that thing, it picks up an extra piece proportional to theta times the magnetic charge. And you might think that violates Dirac charge quantization, but if you work it out, you can still find consistent solutions where electric charges go up in integer units. But you get this effective charge shift. The other thing about this crazy Lagrangian is that you can show that that second term multiplying theta, if you actually sat down and calculated it and integrated it over all of space-time, turns out that it's always an integer. So topological number 2, Pontryagin number. So if theta is multiplying an integer, when you do quantum mechanics, the way it comes into the path integral is e to the I theta times the integer. And if we shift theta by 2 pi, then we've multiplied by e to the I 2 pi times an integer, which doesn't do anything. So that means shifting theta by 2 pi has to be a symmetry of a quantum field theory, no matter what. So we have a magic new symmetry. We can shift theta by 2 pi. And then since we're being really crazy, we could take these two couplings and randomly call them one complex number. So the real part of tau is this proportional to theta, and the imaginary part is proportional to 1 over the gauge charge squared. You wouldn't think of doing that at first, unless you'd read some supersymmetry books. But just say you did write that weird combination. Then you can rewrite electromagnetic duality. Instead of E goes to B and B goes to minus E, you could just say tau goes to minus 1 over tau. that's equivalent to electromagnetic duality. So now we have two magic things we can do to our theory. So we have string theorists like to call electromagnetic duality S. This transformation tau goes to -1 over tau. And shifting theta by 2 pi, that's tau goes to tau plus 1. They call it T. So those are two operations, and they don't commute with each other. And so you can imagine you can get a whole group of things. So if you do all possible combinations of those transformations, you will get that there's a new tau prime, which is A tau plus B over C tau plus D, where A, B, C, and D are integers, and AD minus BC has to equal 1. And this group is called SL2Z, Z for integers, integer-valued transformations. When you do that, it also messes up. Here, J is the electric current, and K is the magnetic current. So you get new electric and magnetic currents that are linear combinations of the old things, but you get an equivalent theory, is the amazing thing. So you have an infinite number of descriptions of your theory of charges or charges and monopoles. And we can say it's a duality because it's not the same theory. It's a different looking theory. It has a different Lagrangian, but it describes the same thing. So if you look at, the reason I bored you with all these equations was just to show this picture, because it's so beautiful. So here is a plot of all possible values of tau. So we have, going up this axis, 1 over the gauge coupling squared. And along this axis, we have theta. And if you see this funny region here, it's like 2 parallel lines and then an arc at the bottom. Mathematicians call that the fundamental domain of SL2Z. What they mean is that if you know what happens in this little piece, then SL2Z maps this piece to, there's an SL2Z mapping of this piece to any other of these triangles down here. So everything that's colored in red is what we would call a weakly coupled theory that looks like the real world. But every spot in red here, there's one there and there and there. There's an infinite number of them. All those theories are exactly the same. So every point with the same color as another point is exactly the same theory expressed in some very complicated different way. I just like looking at this picture, that's all. So if you could solve one of these theories, you've solved an infinite number. OK, so we've come up to the 50th anniversary of Dirac's paper. And to celebrate the 50th anniversary, Sidney Coleman, on the right, wrote a review of monopoles, explaining everything that was known up to that point. And he pointed out that Schwinger, Nobel Prize winner, inventor of dyons, generalizer of charge quantization, Coleman said Schwinger was wrong. Schwinger said that you just calculate the running of the electric and magnetic couplings, and you get the same behavior. So hopefully, since everyone claims to be a particle physics expert, you remember that couplings run, constants aren't, and variables don't. So as we probe the electric charge at shorter and shorter distance scales, the effective charge gets bigger and bigger. Schwinger said when he did the calculation, you get the same behavior. As the distance scale gets smaller, the electric charge gets bigger, and the magnetic charge also gets bigger in the same proportion, exactly the same proportion. And Coleman said, duh, E times G is a constant, because Dirac charge quantization, angular momentum is not going to run. It's got to be half integers. So that means E times G is constant. G has to go the opposite way. If G gets big, electric charge gets bigger, then magnetic charge has to get smaller. So who are you going to believe? We're going to have a poll. OK, how many people believe that Nobel Prize winner Schwinger is correct? 1, 2. How many people believe that Sidney Coleman is correct? Oh, big majority. How many people didn't vote? OK, we're going to see. Because 20 years later, Seiberg-Witten stepped in and settled all of these controversies. So, Witten again. OK, so they looked at a particular supersymmetric generalization of electromagnetism and, well, generalization of the Topological, really. So some SU2 group breaks down to electromagnetism in such a way that there can be monopoles. In the supersymmetric theory, instead of having a unique vacuum, there is an infinite plane of possible vacua, all with the same vacuum energy. So this sheet is a function plotted over this plane of possible vacua. It's parameterized by some complex number. And what I'm plotting in purple here is 1 over m tau, which for normal people is just e squared over 4 pi, the gauge charge squared. And you can see that as you vary over the different vacua, the gauge charge measured at low energies varies, and at some places it has spikes. It blows up at 2 points. How did they do all this magic? Well, they relied on this SL2Z property and supersymmetry, and it allowed them to calculate everything about the low energy theory. And out of the calculation pops an elliptic curve as part of the solution. The elliptic curve is like it describes a torus. The torus has a parameter tau, which is a complex number, which tells you about the angle between if you map the torus to a rectangle, there's an angle between the edges. Tau tells you about, if you put that rectangle on a complex plane, tau is a corner of that rectangle. So tau is hidden magically in this torus. And as you move around in the different vacua, the torus changes shape. And in certain places, one of the torus has 2 cycles. We can go around this way, or you can go around the short way. In certain places, one of those cycles shrinks to 0. At those places, some magnetically charged particle becomes massless. When the magnetically charged particle becomes massless, it makes the electric coupling blow up. And this is a consequence of electric and magnetic charges running the opposite direction. So Coleman was right. So out of this theory, you can get arbitrarily light monopoles. In the gut theories, they only knew how to do things at weak coupling, weak electric coupling. And when you do that, the monopoles are very heavy. But this is a non-perturbative calculation. So you can see where the monopoles can be arbitrarily light. You can make the physical size of this monopole. This hedgehog had some physical size. But if you make the physical size smaller than the Compton wavelength, then you couldn't tell that from a fundamental particle, because you can't resolve things smaller than Compton wavelengths. So as we get close to these special points, these things look like elementary particles. So just for fun, so again, they were just breaking SU2 to electromagnetism in a supersymmetric way. And so the possible vacua are parameterized by some complex number u, and they can just write down the exact mass of the monopole. It's given by some hypergeometric functions as a function of where you are in this plane. So this is like crazy amazing. It's not like I can calculate the electron mass because it's some Yukawa coupling times the Higgs vev. And the Higgs vev I measure one way, and the Yukawa coupling I measure by measuring the electron mass. And that tells me what the Yukawa coupling is, and then I predict the electron mass in terms of my free parameter. This is like, they predicted particle masses non-perturbatively, exactly, all orders. You're not amazed. It's amazing. Seriously, it's amazing. If I say amazing one more time, will you be amazed? Okay, so let's stop for questions. How fast was I going? Oh, we're about halfway. So that's good. We're almost done the review. There's just one more review talk. Any questions on Seiberg-Witten? Oop.
About that, the difference of charge in
the running?
In the running of the charge.
I'll go back.
No, a little more. No, not this part.
I don't know. Not this one.
No. When
Which
you
direction?
said that the charge is runs with the charge of the
This one?
of the magnetic monopole. No, back.
Say when.
Yeah, this one, effective charge. Yeah, sorry, forgot.
Oh,
Is it possible to detect if this happens, or only we can calculate the charge that we have?
well, first find a magnetic monopole, then just measure its charge and theta, and then yes, you can measure it. But you have to have a monopole first.
Okay.
So I guess I should say that several people have discovered monopoles, but no two people have discovered monopoles with the same charges. So we don't actually know if there are any monopoles yet. But some people think they found them. But no one else believes them. Okay. Since we're covering all possible topics, we'll cover dark matter too. So everyone's seen this picture. I'm contractually obligated to show it whenever I say dark matter because the second author was at UC Davis. Okay, so my advisor had this idea that we could have particles that we don't know about that have some strange coupling to us that's very weak, and then it would be hard to find, and that's why we don't know about them. So his idea was we could have a dark photon. Dark photons could couple to dark electrons, but we could be sensitive to them because it's possible to write yet another invariant term. We could have the field strength of our photon contracted with the field strength of the dark photon. And in plain English, that's electric field, our electric field dotted into the dark electric field, and our magnetic field dotted into the dark magnetic field, suppressed by some coupling epsilon. So either these dark photons could have a mass, then they could be the dark matter, or they could just couple to some other particles that are heavier that are the dark matter. Lots of possibilities. But as you know from previous slides, this is not the only thing that you could write down, right? It's the only thing that appears in dark matter reviews. But you could have written something that looks like that theta term. You could have written E dotted into B dark and E dark dotted into B, our magnetic field. So why wouldn't you do that? Who are the dark matter experts here? No one admits to it. No one is studying dark matter. Okay. So what happens if you introduce this coupling instead is that the dark electric charges inherit magnetic charges under our photon. There's a little bit of math to show that, but it follows from that SL2Z again. So But now these magnetic charges are proportional to epsilon. Epsilon is not an integer. It's some small number. So we have fractional magnetic charges. So I've given you enough history of monopoles so you can predict what the resolution of this seeming paradox is. This is the test portion of the talk. Anyone know what the answer is? It's contained in the previous slides, just to see if you're paying attention. I'll give you a hint that this only works, they only get magnetic charges if the dark photon has a mass. And so there's some kind of condensate. And if there's some kind of condensate, then these charges get confined, because Tuft and Mandelstam told us that already. And Seiberg and Witten also confirmed that as a little twist on their big story. If they break the supersymmetry, then they see that monopoles condense and you get confined electric charges. So Tuft and Mandelstam were also A-OK. So in this case, when the dark photon has a mass, these fractional magnetic charges confine. If they're confined, then there's no problem with the Dirac charge quantization because they're neutral. OK, that's going to be the end of history lesson. Any other questions? So after all that, there were three things that didn't work. The first is Weinberg, actually in the 60s, calculated what happens if you scatter an electron off a monopole. And he got an answer that the amplitude violates Lorentz invariance. Pretty disturbing. Second problem is a little more subtle, but it turns out that if you have both electric and magnetic charges, then you know what the individual states are, because Wigner told us how to do that in the 1930s. And everyone assumed that if you have two particles, you just take a product of those two states and you're done. Doesn't work. So that's problem number two. And the last problem is in the heroic age of guts. People got very excited because they found out that if you scatter a proton off a gut monopole, the proton will decay. So it has a fancy name, monopole catalyzed baryon violation, baryon number violation. So that was very cool for a while. And then Callan noticed that if instead of a proton you sent in a positron, then everything went to hell. And his calculation said that you get half particles out. Well, first of all, half particles don't make any sense, but letting him continue, so he said either that means you get half of this one half the time and this other stuff the other half of the time. So that would violate, in his answer, violate charge conservation. But on average, charge conservation would be upheld. So I don't know about you, but those are both crazy. There's no half particles. Charges are either conserved or they're not. OK, so these, as you can see, those are very old things, and no one knew the answer until a few years ago. So I'm going to tell you the answers now. So here's Weinberg's calculation. It's in this famous paper. If you ask your professor or friendly postdoc, they all remember reading this famous paper. Weinberg derives Maxwell's and Einstein's equations from quantum field theory, first principles, without using a Lagrangian. So because he's Weinberg, he can do things like that. What they don't remember is at the very end of the paper, he says, and now we'll apply all this fancy formalism to monopoles. And he calculates the scattering of an electric charge off the monopole. And what he finds is that the amplitudes are not Lorentz invariant. And so his conclusion is that, therefore, monopoles can't exist. Which, in 1965, you could say that, because no one had seen a monopole. But 10 years later, people had shown you how to make a gut monopole. So monopoles can exist. So there's something wrong with Weinberg's calculation. So remember, Dirac worked out what the vector potential is. So if we just have a monopole sitting here, we can just use this vector potential, calculate the scattering amplitude. I wrote it down for you. Don't look at it. It's really ugly. And it must be wrong, because the answer, the amplitude depends on this vector n. Remember, the magnetic field didn't depend on n. N was just an arbitrary gauge choice. So this is not even gauge invariant. So not even wrong. It's just total garbage. So very disappointing, Steve Weinberg. Maybe have a wonder how he got tenure at Berkeley and then got promoted to Harvard. Okay, Steve Weinberg was a great guy. He's much smarter than me or anyone I know. But even Weinberg makes mistakes, so when you make a mistake, just remember, even Weinberg makes mistakes. So Dirac would have said that, of course, you're just going to get nonsense, because Dirac had tried to work out what the Lagrangian is. Weinberg didn't have a Lagrangian, so it's much easier to make a mistake if you don't have a Lagrangian, as we know from helicity amplitude methods. So Dirac said, I know the Lagrangian. You just take the ordinary field strength, E's and B's, and you have to add this extra piece, G. This extra piece, G, is some non-local integral of the magnetic current. So the theory is completely non-local. And so that means you shouldn't be able to do anything, right? Anyone know how to do non-local field theory? Is that covered in any courses? No, it's hopeless. So sometimes you'll hear string theorists say mutually non-local when they don't want to calculate something. That means this mess. There's a mess, and no one can deal with it. Fortunately for us, this is all about writing down gauge potentials, and gauge potentials are gauge dependent. So there are many ways to write gauge potentials, and you just have to find the right one that makes the calculation easy. So as Wanziger said, I only know how to do local field theory, so I have to have local interactions. So if I have a potential that couples to my electric current, I will need another potential that couples to the magnetic current. Then I will have local interactions. Then I will be able to do something. The problem is that now you've doubled the number of photon degrees of freedom, but there's still only 2 polarizations of the photon. So you have to mess around with the rest of the theory in order to project out all the extra stuff. And you can do that by writing the field strength, E's and B's, in this complicated way involving some vector n, in such a way that it projects out half of the degrees of freedom. But at the end of the day, you get back the correct Maxwell equation for the electric current and the analogous Maxwell equation for the magnetic current. So this is the real way to do the calculation, at least to get started. So what do we have to do? So Weinberg was scattering an electron off a monopole. So if he exchanges one photon, there's an E from the electron and a G from the monopole. But E times G is quantized to be half integer. So that's not a small thing. So if I added another photon across, that's also not any smaller. usually when you add more photons, there's an E on both ends. And E times E times E gets small rapidly. So you can just keep the first term. In fact, you keep all the terms that have the same number powers of E. Those are guaranteed to be gauge invariant, right? Because they're functionally independent. So here, E times G doesn't have a small parameter, so you have to include all possible orders. So you have to sum up all possible photon exchanges to get a gauge invariant answer. Unfortunately, some smart guy named Steve Weinberg told us how to do that. If it's only soft photons, which means photons with energies that are small compared to the charged particles, then you can sum up all possible soft photon emissions and exchanges, and it exponentiates, and it's a very beautiful, simple calculation. So we just have to do that now, including magnetic charges. The magnetic charge can radiate this other gauge potential. And there's also processes where we exchange the photon between, if we have two electric charges, you can sum up an infinite number of these as well. They also exponentiate. And so there's some formula that you can find in Weinberg's book. Don't look at it. But the final answer is you get an exponential factor. And when you measure scattering, this is actually verified experimentally. So it all works. Now we just have to do it in the case where we have electric and magnetic charges scattering. So we get a more complicated looking integral. It's got crazy 4-index epsilons lying all over the place. It's got vector n's, which represent the direction of the Dirac string lying all over the place. And now we're starting to get worried because the direction n is a gauge artifact. And we want to see that the amplitude is gauge invariant. So if it depends on n, then we've done something wrong, just like Weinberg. So when you do that calculation after exponentiation, what you find is that all the n dependence, all this Dirac string dependence, gets put into one term, which is just a pure phase. And here's the phase you get. It's given by these horrible integrals. But you can see that in the end, you're integrating a delta function. And what the delta function is saying is, how often does, when my electron goes through time, it traces out a world line. My Dirac string traces out a world sheet. And if I take my electron trajectory, I can make a Stokes surface. How many times does the Stokes surface intersect with the Dirac string world sheet? In 4 space dimensions, two-dimensional spaces can intersect at a point. This just counts how many times that happens. So this thing I called L is a linking number. It's a 4D linking number, the analog of Gauss's linking number. And so it's an integer, whatever is going on. This still depends on n. And so you can change what that integer is by changing what n is. But it will change in integer steps. So the final answer is we get some real factor that is independent of n, and all the independence is hidden in this phase. And we remember that if the phase is a multiple of 2 pi, then it can't change anything. And if you look at how the 2 pi's come in, 2 pi times 2 times, this should be E times G, and what we said electric charge was E. Q is some multiple of E. So this is a half integer times 2. This is an integer. L, this linking number, is an integer. So we have an integer times 2 pi times I. So even though there is dependence on this gauge artifact, it's unobservable, just like the Aharonov-Bohm phase around the string. So, hooray. So since we're in Sao Paulo, I have to show a picture of Bohm. But remember their calculation. You can do the Dirac calculation in their formalism by taking the electron in a circle around the Dirac string. And you pick up a phase when you go around the circle. Here, if we go around in a perfect circle, then we only need the phi component of the gauge field. Calculation is very easy. And if we take the limit that the circle shrinks down, so it's just epsilon larger than the string, then that phase is just 4 pi Eg. And so the Aharonov-Bohm phase around the string is exactly this linking number. So this is a covariant four-dimensional QFT way of doing Aharonov-Bohm. Okay, multi-particle states. Usually in quantum field theory class, we say that we have particle, we know how it transforms, it's a well-defined state. We have two particles, we just multiply them together. It's just a product. But when we have electric and magnetic charges, that's not true. So so you remember that an electric and a magnetic charge has some angular momentum. So if you look at this quantum angular momentum with this covariant derivative has a gauge field in it, in the presence of magnetic charges, this thing does not satisfy the commutation relations for an angular momentum. But if you include the angular momentum in the electromagnetic field, the thing that J.J. Thompson told us about, then this mess does satisfy the correct commutation relations. So this is the real quantum mechanical angular momentum, just like J.J. Thompson would have told us if he'd lived to see quantum mechanics. And Dirac charge quantization tells us that the general angular momentum for a dion is quantized in half integer units. So that's consistent with quantum mechanics. Now, Wigner was the one who figured out how to describe single particle states. He did it in 1939. And he used some group theory. And in 1939, physicists said, group theory, that's just some crazy formal math stuff. We don't need no stinking group theory. And it took people 20 or 30 years to realize, oh yeah, we really do need group theory. Wigner was a genius. So what did Wigner do? Let's take a massive particle. It can have a spin in general. So the way to describe it is to do the simple thing, go to the rest frame. It's just sitting there. I can rotate it in 3 dimensions. So the spin rotates if it has a spin. And then I can boost it to any other frame. If I know what's doing in the rest frame, how the rotations leave the state, the momentum of that state invariant, and then I boost, that gives me the most general state. If we have a massless particle, then we have helicity, which you can think of as spin projected on to the momentum direction in the limit of 0 mass. So what leaves the momentum invariant is rotations around the momentum direction, because we don't have a rest frame. There is some direction it's moving in, but we can still do a rotation around that axis. So this gives us SO3 rotation for what's called the little group that leaves the momentum invariant. This gives us a U1, rotations around a single axis. And so the boosted states, once we boost them, there is a rotation that leaves the momentum fixed. So he did all that way back when. And now what's the problem? The problem is we have something with electric charge and something with magnetic charge, and we're going to scatter them or something. We have a state with both of them. So if we go to the simplest frame is the center of mass frame, center of momentum frame, where they're going towards each other with equal and opposite momentum. So what leaves that system invariant? It's rotation around that momentum axis. So this has a helicity describing it. And when we do rotations, so when we have both electric and magnetic charges, there's some angular momentum in the field. And when we know from quantum mechanics, if something has angular momentum and you rotate it, you get a phase. So when you rotate an electron by 2 pi, you get -1, because you get an e to the I pi. which is e to the 2I pi over 2 because it has spin half. So we have to include this extra phase from the angular momentum in the field. So Zwanziger figured out a trick where he could calculate this as long as this was 1 unit of angular momentum. It was a technical trick that only worked for that case. But you can generalize that. And the generalization for any possible angular momentum in the field is called, we call it pairwise little group. And this is the pairwise little group phase that you get from that extra angular momentum. So this two-particle state has an extra parameter. The extra parameter is how much angular momentum you have stored in the field around it. So it's not a tensor product. Now, this is all group theory, and when we did this, our friend said, group theory, we don't need no stinking group theory. We already know everything. So can you actually convince people that you really need this? One way to convince them is that to do what's called a dress state. What is a dress state? Usually in particle physics, we like to pretend that electrons just go off by themselves and that they don't have this Coulomb field around them. But in E&M, electrons, we learned, do have a Coulomb field around them. And if you boost the electron, you boost the Coulomb field. So maybe you might want to take care of that. And the formalism for doing that is called dressing the particle. So what you have to do is sum up all the possible soft photons. So very low energy photons can be emitted or exchanged between particles. If we have both electric and magnetic, we have to include those exchanges as well. So the dress state is the particle plus the coherent state of photons that make up its electric field. So there's some cloud of photons and a Dirac string if we have a magnetic charge. So we have to rotate that whole mess. Amazingly, you can do that calculation. So rotate the photon cloud and the string and do a whole 2 pi rotation, so you get back to where you started. And by doing that rotation, you pick up a phase, which you just calculate from this coherent state. And the phase is exactly what the pairwise little group predicts. So group theory works again. Not a surprise. Group theory always works, but some people aren't convinced until you do the horrible 20-page calculation instead of 2-page group theory calculation. Professors are like that. So one more check. Another way we could check it is just to do scattering the lowest partial wave. So we have a monopole, we have an electron, and the minimal angular momentum we can have turns out to be angular momentum in the field minus a half if the monopole is spinless and the electron has spin half. So we can get if E times G is a half, the minimal Dirac monopole, then we can get J equals 0 state. And the way we do that is the spin of the electron is anti-aligned with the spin in the field, and you take the anti-symmetric combination just like you do when you add 2 spins. So that gives a J equals 0 state. And when you calculate what can happen, if E times G is less than 0, the only possibility is that a right-handed fermion goes to the left-handed fermion, because E times G determines the direction of the field angular momentum. If it's opposite, then you can only have a left-handed fermion going to a right-handed fermion. So this exactly reproduces an old calculation in 1976, 20 pages of solving differential equations. So solving the Dirac equation of electron in the background field of a monopole, finding all the scattering states, constructing scattering amplitude, projecting out into the partial waves, you can do in 3 lines. So it seems to work. Yay, group theory. OK, I'm out of time. Oh, I have 3 slides left. Let's finish quickly. So the last problem was this half particle story. So I'll remind you, Georgi and Glashow were the ones who discovered guts. They said take SU3 and SU2. 2 plus 3 is 5, so this should fit in SU5. And if you look at the details, U1 also fits. So SU2 is 2 by 2 matrices. SU3 is 3 by 3 matrices. That fits into a 5 by 5 matrix. All the particles you see around you are made of electrons, up quarks and down quarks. Quarks come in 3 colors, red, blue, and green. They all fit into the representations of SU5. There's a 5 bar and a 10. And there's even room for a neutrino. So that's a whole generation of particles. If you want 3 generations, just take 3 copies. Good? The point for us is that in the middle of this matrix, there's another SU2 that overlaps, but that's broken when the gut breaks down to the standard model. And it's exactly the kind of breaking that gives us a monopole, because it has to give us a U1 in the standard model. So we have monopoles in this theory, and in the 70s, people said, you know, SU2 is hard enough. We'll just look at the SU2 subgroup and figure out what's going on. So then we just have to worry about the things that transform under this little SU2 that has the monopoles in it. So there's 4 doublets of SU2. Rubikov-Callan said, OK, we've got this monopole. We send in some up quarks in an S wave, just like we did with the scattering the electron off the monopole. The initial state will be in some j equals 0 state, just like before, now just with 2 particles. Forward scattering is not allowed for the same reason as before. If you go through the monopole, then the angular momentum in the field flips, but then you're not in a S wave anymore. So the only possible final state that's allowed is that 2 U quarks produce a positron and an anti-down quark. So if I added an extra d quark here, and in the final state, this would be some pion and a positron. So proton turns into positron plus pion. Baryon number is violated. Well, it was already violated in grand unified theories anyway. That's why people sit and stare at mines filled with water for 40 years, hoping to see a proton decay. But this happens with a QCD cross-section. So it's much, much faster, provided you have the monopole. So if you had the monopole, you could drop protons on it, get free energy, and all our problems would be solved. So please find a monopole. OK, so the last thing. Callan's puzzle is do the same thing, but now with a positron instead of a proton. What do we get out? You'd think that you'd get, if baryon number is violated, one thing you could get is a proton, because that conserves charge at least. So we have our initial state. It's j equals 0. And we have to choose from these possible things. And from the flavor symmetry, you need to choose 1 from each column, if you think about the flavor symmetry. So you would think that if you want to get a proton out, you would choose this. But this guy doesn't have j equals 0. So because he's down here, and these guys are up there. So it seems like it doesn't work. Callan said, let me reduce this to a 2D theory. Then I can do fancy tricks, bosonization, magic. And out of that, I get the final state is this, half a positron and half a proton. Yeah. I don't have to say why that's crazy. It's crazy. So what's the answer? The answer is that it really does go to a proton. What going to 2 dimensions missed is that there's other ways to make j equals 0. So we could take the down quark that wasn't working before. We could make it a j equals 0 with the angular momentum in the field of a U quark. and take that U quark and make it a j equals 0 with the field in the down quark, and do some anti-symmetrization so everything else, all our color and fermion symmetries work. So this final state is perfectly allowed in 4 dimensions. It doesn't appear in the 2D truncated theory, so not surprising he can't get the right answer. So overall, j equals 0. Again, we claim group theory solves the problem in 3 lines. People still want to see, where's the proof? Where's the 20-page calculation that proves this happens? Still working on that. So conclusions. So Lorentz violating terms from soft photons exponentiate to a phase. Weinberg's gauge dependence is hidden in a 4D topological number. So he was just lazy and only worked to first order, and he couldn't see that it was an exponential. Rotations shift the phase. If we have both electric and magnetic charges, we get a phase shift predicted by the pairwise little group. And the pairwise little group fixes scattering amplitudes. In particular, gets rid of Callan's half particles. And there's just 10 more years to the 100th anniversary of monopoles. So hopefully more exciting developments ahead. Thanks.
Thank you, John. So questions?
Hi. So really quick question. You said that every time that a single SU2 breaks down to a U1 electromagnetism via spontaneous symmetry breaking, you always get a monopole.
It's an allowed solution, yeah.
It's an allowed solution. This doesn't happen in the standard model because it's not one single SU2 breaking down. It's the SU2 times U1 thing. And
Right, so there's already a U1 before you start, so you're not making a new U1.
On your favorite slide with the colorful plots, can you trace out where RG trajectory would go?
Sorry, trace out what?
An RG trajectory for the E and G going as a constant? I mean, do you get...
Well, you could if you have to tell me how many electrons and how many monopoles.
Yeah, but in principle, just for NF equals 1 and 1, for example.
Well, say that it runs the same way as in the standard model. So it starts at long distances, we have weak coupling, and it runs to stronger coupling, right? So it would run up this way.
Yeah, but I'm also wondering what happens to a possible Landau pole in one of the couplings. Is there some interpretation?
Well, once you have both electric and magnetic charges, you have a possibility of a fixed point. So depending on your theory, you could hit a fixed point instead of a Landau pole. So then we wouldn't need guts.
Yeah, but is that a point, is that fixed point on this?
Well,
known
this
in some
coupling
sense.
goes from 0 to infinity, so it's definitely on this plot. Right, here's coupling equals infinity, and up in that direction is coupling equals 0. So it's somewhere between 0 and infinity.
Yeah, I mean, is it attractive? Is it repulsive? Has someone done the RG analysis in this SO2Z?
People have done it in supersymmetric gauge theories. So what's their name? Our friends. Argyris-Douglas. It's called the Argyris-Douglas fixed point. But people only trust the calculations in supersymmetric theories because there's non-perturbative things going on. So I guess I should say Holger Beck-Nielsen has calculated in a non-supersymmetric theory, and he claims that it's on the edge of reliability that you could have a fixed point with one electric charge and one magnetic charge.
More questions?
So how do we find monopoles?
Well, I mean, inflation was designed to get rid of monopoles. So if we have a gut and then there's inflation afterwards, inflation is supposed to reduce the number of monopoles to 1 per Hubble volume. So you have to get very lucky if that's the story. If there are dark monopoles, then they're confined. If the confinement scale is low enough, then they could be macroscopic lengths. So then you could hope to detect them, but instead of detecting a single monopole, you detect a fractional monopole and then the anti-monopole, assuming they're polarized. So you have to get them in an excited state for them to be polarized, right? Because hydrogen ground state is not polarized, but if you excite it, you can make it polarized. So we did some calculations that if they go close to the sun, they can be excited, and then if they hit the Earth, the magnetic field could align them, or you could put in an external magnetic field. And then you'd need some detector like an interferometer or a squid. So yeah, no experimentalist has started working yet. So at this rate, we'll never detect them.
Have the discovery of the magnetic monopoles in condensed matter physics changed our view from the theory and phenomenology?
Well, far be it for me to criticize condensed matter physicists, but when they say they discovered a monopole, what they discovered was that if you have a very long, thin solenoid, it has a north pole and a south pole. And if you make the solenoid long enough, you can just look at the North Pole, and it looks like a monopole. So I think someone discovered that before. That used to be a physics demonstration. It's also how people, when people were trying to figure out what the equations of electromagnetism were, the way they tested the magnetic field was to have a long, thin solenoid so that the other pole was very far away, and then test that magnetic field by itself.
Okay, great. Thank you.
More questions? Okay, then now that we know all about monopoles, homework for you guys, due tomorrow, find a monopole. So let's thank John again for the very nice colloquium. Thanks, John. It was very nice.
Oh, thank you. I can take this off now.
You can take that now.